Jorgensen and fellow proof students. My name is Ryan Schulze, and in this video we're going to be covering oral presentation number 2. Now, oral presentation number 2 is specificating the relationship of a function on integers with its derived difference formula, being that d of n is equal to f of n minus f of n minus 1. What we need to do in this video is we need to find a value of f of n, and we need to validate it by proof by induction. Knowing a bit of information, being that f of 0 equals s and d of n is equal to pn squared plus qn plus r, we need to find f of n and prove it. I am going to propose that f of n is in the terms of an cubed plus bn squared plus cn plus d. So f of n is a basic cubic function. Why am I going to propose that? It's because d of n follows a relationship that is always 1 degree smaller than f of n. For instance, say that f of n was an squared plus bn plus c, a square relation. When you find the d of n here, this is the f of n term, and this is the f of n minus 1. Then all these terms cancel out here, and then you're left with d of n is equal to 2an minus a plus b. This is of degree 1, meanwhile this was of degree 2. Therefore, it should follow suit that if we have a degree 3, then our difference will be of degree 2. That's why I'm going to propose that f of n is a basic cubic function, and then all we need to do is solve for a, b, c, and d, and we'll find f of n, and then we can prove it by p and I. So let's begin to look for these coefficients. Just looking at this, we know that when we have f of 0, this zeroes out, this zeroes out, this zeroes out. Therefore, we can immediately tell that d is equal to s. Now what we're going to do is we're going to solve for d of n using these terms, and then we're going to find them in terms of p, q, and r. So d of n will then equal an cubed plus bn squared plus cn plus s. And then it's going to subtract a of n cubed minus n 3n squared plus 3n minus 1 plus bn squared minus 2bn plus b plus cn minus c plus s. Therefore, we get that d of n is equal to 3an squared plus 2bn minus 3an plus a minus b plus c. So this is what our d of n is equal to. Now, in order to find a, b, and c, and then find them in terms of p, q, and r, we just need to look at the values of the degrees. So second, first, and 0th degree, and then we just need to group them as accordingly to our d of n that we have given to us. So looking at this, we know that 3a is equal to p. We know that 2b minus 3a is equal to q, and that r is equal to a minus b plus c. Okay, so let me erase this a bit. Just doing some basic substitution in algebra, we know that a is equal to p over 3, so we're just manipulating these. B is equal to q plus p divided by 2, and then c is equal to 6r plus 3q plus p divided by 6. So then we can go back, and then we can substitute them into f of n here. So that means our value of f of n is equal to p thirds n cubed plus q plus p divided by 2, and squared plus 6r plus 3q plus p divided by 6n plus s. That is our f of n. Now, we want to make sure, does this hold true for f of 0 equals s? So when we plug in 0, this zeroes out, this zeroes out, this zeroes out, so look at just s. So we can, just looking at this, we know that f of 0 equals s, which is perfect because in order to use induction, we need to have a base case and make sure that it holds true. While it's not directly stipulated, we need to use a non-negative integer. Therefore, our base case is going to be with 0. So we already know, hey, this comes out perfectly to s. Now, with proof by induction, we need to have two sides, a left hand and a right hand. So what we're going to do is we're going to manipulate this function up here. So we're going to say that f of n is equal to d of n plus f of n minus 1. And in order to prove our base case, we want to say that f of 0 is equal to d of 0 plus f of minus 1, which we can easily prove. So we know that this is s, so this is p times 0 squared plus q times 0 plus r plus p thirds negative 1 cubed plus q plus p over 2 times negative 1 squared plus 6r plus 3q plus p divided by 2, and it's negative 1 plus s. Now, we just need to make sure that this comes out to just s, and that our left hand and our right hands are equal to each other. This zeroes out, so we have r minus p over 3 plus q over 2 plus p over 2 minus r minus q over 2 plus minus p over 6 plus s. So the r's cancel out, those q's cancel out, and then a third and a sixth comes out to a negative 1/2, and we have a positive 1/2. So those cancel out. So this is equal to just s. So the left hand and the right hand side of the base case both come out to f of 0 equals s. So dn of 0 plus f of 0 minus 1 also come out to s. Perfect. We've begun the first part of our inductive step. Now we're going to assume that for all n equal k, this relationship is going to hold true. However, now we need to show, is it going to be equal for n equals k plus 1? So we're essentially going to do the exact same thing. We're going to go back into these functions, and we're going to substitute n for k plus 1, and if they're equal on both sides, then this is equal. So then we're going to have f of k plus 1 is equal to d of k plus 1 plus f of k. This is f of k because, we plugged in n here, and this is originally n minus 1, so n minus 1 plus 1, since you with the k, that gives us just k. Okay, so let's go ahead, let's tackle this right hand side first. So we have p of k plus 1 squared plus q k plus 1 plus r, and then we have our original function here. So then we need to go into here, and then we need to expand this out, and we need to find out what is this all equal to. So this is just going to take a little bit of algebra. Alright, so then we're getting all this, we're going to get p thirds k cubed, okay? And then we're going to have 3/2 pk squared plus 13/6 pk plus p plus q over 2 k squared plus q over 2 k 3/2 qk, my apologies, plus q plus rk plus r plus s. So this is what that right hand side is equal to, and I'm going to leave this here so you don't need to make a mental screenshot. So now we need to find out what does f of k equal to. So we have p thirds k plus 1 cubed plus q plus p over 2 k plus 1 squared plus 6r plus 3q plus p divided by 6 k plus 1 plus s. So once again, we're going to need to open up all of these and then find out if it's equal to this. And upon doing the math, we need to expand this out. So now I'm going to condense this and I'm going to go straight into what the answer is going to be. As you can see here, we already have p thirds k cubed plus 3 halves pk squared plus 13/6 pk. So this is already beginning to line up very nicely. Plus p plus q halves k squared plus 3q over 2k plus q plus rk plus r plus s. So as we can see here, the right hand side and the left hand side do in fact equal each other. So the inductive step shows that this is not only true for when n equals k, but for n equals k plus 1. Therefore, we know that our original function that we proposed, that f of n is equal to p thirds k cubed plus q plus p over 2 k squared plus 6r plus 3q plus p over 6k plus s. So we know that this is valid, because by proof by induction, the next inductive step is always going to be true, and before then, the base case is true. And that concludes this presentation. I hope you enjoyed. Thank you very much.